Hey, what's up, guys? I'm going to do a little PowerPoint on some atoms, get a little bit more in depth. We've been a few weeks into atoms now, so it should be getting a little bit clearer for us, and we'll get a little bit more moving forward. So, starting off, take a look at our essential question. How and why has the atomic theory changed over time? How can we describe the molecular motion of the states of matter? All right, so get going here. Be able to explain that atoms are the smallest unit of an element and are composed of subatomic particles. So last week we kind of jumped into the periodic table. You guys saw that periodic table has all those elements, right? An atom is the smallest unit of each element. So we can have an atom of hydrogen, we can have an atom of oxygen, we can have an atom of uranium, right? So all of those elements, the smallest form of them would be one atom. And that would be the mass on the periodic table for each element is the mass of one atom, right? It's AMU, atomic mass unit. You guys are going to analyze models of scientific theories of atoms. So one of our goals for this chunk is for you guys to be able to actually model atoms. And remember, your end of the quarter project is going to be building a atom in Minecraft. So you need to be able to model these things. You need to be able to draw models and visualize these models because you're going to need to be able to actually build one in Minecraft. And then we're going to analyze models and describe the motion of particles in solids, liquids, and gases, right? So a solid, like a frozen block of ice, a liquid, like a cup of water, or a gas, like if you're making tea, and you see the teapot start to blow steam out, right? That would be water as a gas. Matter is anything that takes up space and has mass, right? So all matter is made of atoms. And we said that matter is just stuff, right? So anything that is stuff is atoms, okay? Atoms are the basic building block of matter. They make up everything around us. Your desk, the board, your body, everything is made of atoms. Atoms are too small to see without powerful microscopes. Now you might read that and say, we're made of atoms. I thought we were made of cells. And you're right, right? We are. Living things are made of cells. But atoms are within cells as well, right? So, like take your cell membranes, like the outsides of each of our cells. The cell membrane is it's a fatty lipid it's a phospholipid bilayer, right? So you think of phospholipid, phosphate, phosphorus, right? Phosphorus is an element. There's atoms of phosphorus within that phospholipid bilayer. I know those are big words, but our cells are made of atoms, right? Atoms are the Legos that make up this Lego world we live in. All right, so we have the nucleus, we have the electron cloud, right? We already talked about that. That's from last week. Nucleus has the protons and neutrons. Electron cloud has the electrons. Protons are positive, neutrons are neutral, electrons are negative. You got that right there. All right, so because we can't see atoms, we use models to teach about atoms, right? And the great thing about science is that we change over time. When we learn something new, we change our theories. That's what's so fantastic about science. We don't just say this is the way it is. As new evidence presents itself, we change our theories. Just like we used to think that the world was the center of the universe, we learned that's not the case. So we don't teach that anymore, right? Because it's not true. So atomic theory, our models have changed. Our models have improved over time as technology has improved over time. So these models will look different throughout the history. Right, so John Dalton, he was our first guy. He said everything was made of atoms, so he was right. He said that atoms are too small to see. He said they're indivisible and indestructible. So he said that an atom is so small, it's the smallest thing, you can't break it apart. Right, and we know that's not true. We have protons, we have neutrons, we have electrons. All atoms of a given element are identical. So he thought that every single atom was the same once it was in the same element, right? That's kind of true for our learning, but we did learn last week about ions, right? Ions can have extra parts, and that would make it not identical. J.J. Thomson, he found the electrons, right? He predicted there also must be a positive particle to hold the electrons in place. So that changed our model, right? He said, oh, it's not just this one indestructible piece. There are other parts within it, right? He didn't know about protons, but he said there had to be something positive if this negative thing is held in place. Rutherford, that's Ernest Rutherford, he discovered the nucleus of an atom and named the positive particle protons. he concluded that electrons are scattered in the empty space around the nucleus, right? So he had this idea that there's protons in the middle, there's electrons on the outside, and those things are just kind of scattered around there. James Chadwick discovered neutrons are also located in the nucleus and that they have no charge. Niels Bohr, this is a very important model, it's a famous model. He concluded that electrons are located in planet-like orbits around the nucleus in certain energy levels. So if we take a look at that, that is the model that we use to draw. Like you're going to see a lot of Bohr models to represent atoms because it's hard to draw the cloud, right, where things are moving within the cloud. Because those electrons aren't just confined to these shells. They move around a little bit within them. But to draw them, it's a lot easier if we can represent those electrons in stagnant places, right? So we can count the electrons, we can count the protons, we can count the neutrons, we can see what we're actually modeling. So Bohr models are big. That's going to be the one we draw the most. All right, so now we get to our modern atomic theory. And we say they don't orbit in these nice little clean orbits, right? It's the electron cloud. But they sort of do stay to their shells. But these orbits aren't perfectly neat, right? So neither are our orbits in space, but they do follow like in outer space, like our planetary orbits, but they follow the same path. The electrons don't necessarily follow the same path. They're all over the place, right? So getting into the states of matter, we've said that atoms make elements, right? Elements, the smallest form is a single atom. So if I have a block of, let's say, oxygen, okay? We could have solid oxygen, we could have liquid oxygen, and we could have gas oxygen, okay? So for everything within the periodic table, we can have different states of matter, solid, liquid, or gas, okay? Now with that, it takes energy to change between these states of matter, right? It's a lot easier to freeze ice than, say, to freeze oxygen, right? I can take a cup of water and I can put it in the freezer and freeze it. But if I just close the freezer, you're not going to all of a sudden have a block of oxygen that just freezes and falls to the bottom of your freezer. Right? So these things change states or have phase changes based on different conditions. So like on Earth, water is a liquid, right? If you were on, say, one of the moons of Jupiter or one of Saturn's moons, right? Like Titan, we say has oceans, then a lot of those are ice for so much because the conditions there are much colder. There's less pressure. There's a lot of things that change the states. So we have solid, we have liquid, we have gas, right? The particles in a solid are packed, right? So if you think about it, like think about your phone, right? It's not like it's moving all over the place like a cup of water. Like the water that's in my cup is splashing around. This is a solid, but they're not totally still. These atoms are still moving, right? They're vibrating in place because these atoms are interacting. The electrons are constantly moving. These atoms are all vibrating, but very, very tightly packed into place. They have a definite volume and a shape. So like my phone's not just going to change volume or shape as long as I keep the conditions the same, right? So particles in a solid, right? How do they move? They just stay for the most part. They vibrate very slowly, or they vibrate quickly, right? But they don't move around a lot. All right, so the particles in a liquid are close together, but they move and they float past one another. So these molecules are, they have a definite volume, right? They're not going to like expand or contract, but they take the shape. So if I have a water balloon, I can squish that water balloon around, right? But if I squish it too tight, it's going to pop because that liquid has a definite volume, right? I can't squeeze that volume down, or I can't expand that volume out, but I can move it around. I could squish that water balloon and change the shapes. I don't know if this will work with PowerPoint. Nope. All right, so gases, right? Gases do not have a definite shape or volume. So think about like a balloon that's blown up, right? The gas in there, the reason that balloon stays expanded is the gas molecules are bouncing all around, right? They keep that balloon pushed out. So when they're placed in a container, it fills up the container and it spreads out as far as possible, right? So like say you have a pot of water and you put the lid on, right? It's going to fill up. That gas is going to fill up. Eventually, that gas is going to find ways to get out, right? You see that steam kind of popping off, coming out from the lid. If you didn't let any pressure out, we would create some sort of explosion, probably not with boiling water, right? But that steam needs to escape somehow. So in this case, these gas particles, they're going to be bouncing all over the place. And you guys are going to have an activity to look at that as well. All right, so we go from solid to liquid to gas. We can also go from gas to liquid to solid, right? So as the molecules speed up, we go from a solid to a liquid. They speed up a little bit more, they become a gas. Think about a pot of water, or think about putting an ice cube in a pot on the stove, right? It starts as an ice cube, it's solid. As it starts to gain energy, those molecules start to move a little bit more. And now that ice melts, and now it's liquid that takes the form of that container. And as it heats up more, now those gas molecules start to escape, right? They pop off and they start to float away. Or if we cooled it down, we could take some water vapor, we could cool it down, make it come back to water, put that water in the freezer, and now we have an ice cube, right? That would be back to a solid. All right, quick, nice and fast, right? It was only about 11 minutes. Go back through, pause where you need, take notes where you need. Remember, we're in the heart of our learning right now. This is the kind of information that you're going to need to be able to do the activities moving forward, right? I don't want to hear from somebody saying, I don't know how to do the lab because I don't know about states of matter. I'm going to say, all right, pop on over, watch video number, Video number 3, I think, and get that information, right? So we got to pull all this information from different places. You guys are doing great so far. If anybody needs any help, needs any questions, especially you digital kids, reach out to me, right? I'm here to help you guys. This week, hopefully you guys got what you needed to get. We had a couple videos. We've got this video as well with the PowerPoint. We got a couple games that we're playing this week. You have that Atom Touch game, I believe. And then we have the game where you're actually the little guy who shrinks down into the nuclear world, right? And you're actually going to move around, and you're a proton, you have a positive charge, you move the other protons around, kind of see how these things interact. So hopefully you guys are getting something from this. If you have any questions, reach out. Hope you guys are doing great. Take care.